G'day, in this video we're going to be looking at polarized light and Malus's law, which applies this concept. So we're looking again at inquiry question 2, particularly we're looking at how we can use the light wave model to explain polarization and make predictions about how polarized lenses work. That is all summarized and encapsulated in dot point 7.2.4. So we're going to be doing some investigations in class to show Malus's law, which is all about comparing the intensity of light as it passes through one polarizer and then the next. So some key learning intentions today. We're going to be looking at light polarization and how it fits within the wave model. And then we're going to qualitatively and quantitatively investigate the interaction of light as it passes through two polarized lenses, which again is defined by Malus's law. So a polarizing lens, essentially it blocks some of the light that enters through it. What you can see here is essentially regular light. Light is coming in where the oscillations of the electric and magnetic field are pointing in all sorts of directions, right? We've got a beam of light, there's lots of different waves coming through and they're all orientated in different ways. Particularly when the light is passing through one of these polarizers, which kind of looks like the diffraction gratings that we were talking about last lesson. They're not the same, but they do diagrammatically look quite similar. The specific thing here that we need to focus on is that these polarizers will block the electric field of the light that's attempting to pass through it. So if I had some light that was moving horizontal like this, it's all going to get blocked by the lens itself. And because the electric field isn't passing through the lens, then the magnetic field, which would be moving parallel to the lens, wouldn't pass through either. However, if you had some electric field that was moving directly parallel with the polarizer, that would freely pass through. And once it gets through, then the magnetic field on the other side would start oscillating horizontally. However, as we already started talking about at the beginning, not all light will have an electric field that's either oscillating directly parallel to the lens or perpendicular to the lens. We have some that are oscillating at various angles. And when we're looking at that oscillation at those different angles, essentially we can break up the oscillation into two components. So let's say that I've got an oscillation that's going this way, for example. There's going to be a vertical component of oscillation and a horizontal component of oscillation. And if this was to pass through the first polarizer where it's lined up vertically, only the vertical component would pass through. The horizontal component would be blocked. So for a lot of the light passing through a polarizer, some of the light or some of the component of the light will be blocked and other components of the light will pass through. And then essentially the resulting light that you get at the end is an addition of all the light that ends up passing through the lens. Something interesting though is now if you have polarized light where it is all oscillating in the same direction and you place another lens but 90 degrees to the first one, it's now going to block all of this polarized light and stop all of it from passing through. We'll demonstrate this in class. We'll take two polarized lenses and set them up so that they do completely block out the light, but this is something that we need to be conscious of as well. So this brings us to Malus's law. We're not just talking about the idea that light can be polarized and talk about qualitatively how that actually works, just like we talked about before with our components, but now we're also looking at what happens to the intensity of the light as it passes through a second polarizer. We've already concluded that if the two lenses are 90 degrees to each other, there'll be complete blockage, but there is a mathematical law that supports that. In this formula I equals I max cos square theta, there's a few things to keep in mind. I max and I naught are the same thing. So in your data sheet, it's written down as I max, right? But in other sources, you may see it written down as I naught. They are written both ways. They are the same thing, but the key bit to know here is that the intensity of light after passing through the polarizer, which is the first lens, is I max. All right, that is the maximum intensity that's going to be experienced either at this point or this point. Not before, but after the first light passes through the first polarizer, this is the maximum intensity that can be experienced either here or here. Next is theta. So theta here is showing the angle between the first polarizer and the second polarizer, which we call the analyzer lens. So that is our angle here. Again, you might see slightly different notation, but in your data sheet, it is written as theta. It's this angle here. So in this diagram, for example, it looks like we're working with approximately a 45-degree angle or thereabouts. We then also have this cos square theta here. It may not be something that you've used before. Essentially, we're taking cos theta and then we're squaring whatever that number is in your calculator. I would probably write it down like that, with cos theta in brackets, squaring the whole thing. So, some conclusions to make from there. If theta is equal to 0, then cos theta is equal to 1. Essentially, what that means is there is no change made to intensity. What that would mean is that the polarizer and analyzer would run in the same direction as each other, which means as light passes through the polarizer and it's oscillating vertically, when it comes to the analyzer, because it's also pointing in the same direction, there's going to be no additional blockage. Therefore, essentially, I max times 1, or 1 squared, is I max. There'll be no change to intensity. But as we established before, if theta is equal to 90, so the analyzer goes along like this, so all the lines are going from side to side instead of up and down, then that would mean that cos theta is equal to 0, and 0 squared is 0, which means that when you multiply I max by 0, you get an intensity of 0 at the end. That means that no light passes through. However, there's going to be different amounts of intensity that passes through as we move our analyzer and rotate it from 0 degrees to 90 degrees compared to the polarizer, and that's going to lead to different intensities, and essentially it's related together in this equation. We will have a look at unpacking that practically together. Thank you very much. In the next video, we're moving on to inquiry question 3. We're about halfway through this module so far, and we're going to be focusing on blackbody radiation and Wien's law. And this is our first little look into starting to talk about light beyond describing it as simply a wave. We're going to be getting into what we know as quantum physics. It's a much scarier word than it is on first inspection, because when we look at the basics in this Year 12 course, it isn't actually all that scary, but I'll hope to prove that to you in the next video. Until then, have a good one.